Yeah. Good morning, everybody. Welcome you all. Since this is my first lecture in the series of 2 weeks expert lecture series of research techniques in ICT, I welcome you all. And this 2 week lecture is being organized by his computer science department and electronics and communication engineering department. Now, these two departments together are, the pillars of School of ICT. And we have been organizing a lot of lectures, web series, and expert talks. And this is another feather to the cap. In these 2 weeks, you're going to study a lot of things like mobile networks, routing, blockchain, modeling, and other things. Since this is the introductory lecture, I'll just want to talk about what research is, what are the difference between a research, and how to go about doing a research, how to start a research, what are the different approaches of doing a research, and then also, is there a defined way of doing a research, or we have to pursue a research in a set format? So there are a lot of queries which students come up to me, and we all discuss all these things. And over the years, I've been teaching this subject, and in fact, I have guided some of the PhDs, 8 PhDs, and each with having a good publication. So this is a learning experience which I'm going to share with you today. So what research techniques in information communication technology is all about. Now, when we say research, normally the things come that we are researching something. And in fact, this word has actually come from this two words. And a strict definition in the scientific research says that it is a study in order to prove a hypothesis. Normally students, when I ask them this question, what is a research or a scientific research? They say, do you want to prove an hypothesis? And that is why there is a research. Or there is a series of steps. We want to formalize a protocol. Any process we want to formalize a protocol, that is doing a research. Or we want to have an interpretation, an opinion of certain factual phenomena, then also it is a research. But it's a real scientific, it may be economical, historical data, or whatever. We interpret it in our own form, that is a research. In fact, all this is research, but it is all organized and it undergoes a lot of planning so that whatever research we are aiming at brings out something new. It contributes something new to the organization, to the society, to the world. That is the linchpin, that is the novelty. Another question which props in the mind is, how is research in ICT different? When we say research, research means doing a historical research also, social sciences research also. Why this topic, research in ICT, information communication technology? Dear participants, we need to understand that IT, there are two concepts. IT can be used as a tool to get into the research of social sciences or historical or technology related researches, or it can be research in the area of information technology. And these areas include a lot of areas like cloud computing, software engineering, IoT, networks, then mobile networks, then sensor networks, web of things, and so many other plethora of things which revolve. IT is actually an application-oriented stream which has to handle so many researches. So how is it different? Is it something like I do an excavation in Mohenjo-daro and Harappa and find out some artifacts and try to find out how exactly the culture of this particular place was? Or is it different from that? It is definitely different. ICT helps us in doing a exploratory sort of research. I can explore the phenomena. If you can see this particular picture, there is a book lying and there is a secondary data in that book. That data and everything has been analyzed with the help of computers, and then we analyze this data and give a meaningful interpretation to it. So it becomes we formulate some hypothesis out of it, we formulate some interpretation out of it, and then it is an inferential research also. We also try to see the cause and effect of the research. We diagnose a problem. So any problem which we want to diagnose becomes a research which is using an ICT tool, information and communication technology tools. So that is a research. Then there are different types of research. To hook on and get on to that research is very, very important to understand the different types of research, because these are terms we normally use when we compile our reports, when we talk about research. We have a descriptive research. Now, when we say a descriptive research, it involves a lot of surveys, fact findings, inquiries, and it is more of related to social sciences, business research in a nutshell. ICT deals with analytical research. Analytical research, here the researchers use facts or information which is available and which is not available. Even if it is not available, we try to make it available by doing some exploration and analyze to make critical evaluation of the material. We do a critical analysis of this material, and there are a lot of tools available with us. So it is an analytical. We come out with some phrases like we had given an analytical interpretation to our results. That means theory and practices which were existing, we have utilized them and we have used them to give some inferences. A research can be applied or a fundamental one. Applied research is one which is pertaining to an immediate problem faced by a society. It is applied. Today we are going through a tough phase of corona pandemic, and then we want to know what is the drug, which drug is more effective in treating the patients. It is applied. Which particular algorithm will work best in this particular scenario? It is applied. Which cloud computing technique will be best suited to handle such sort of a data, or to find the queries on that particular data? That is applied. What queuing model is being used to manage the queue lines? Again, it is applied. A fundamental research is one which is mainly concerned with the basic or pure sciences. It may be a natural phenomena. It may be pure mathematical research or pure sciences research. In fact, it also includes the human behavior research, which is talking about the generalization of human behavior. That is also fundamental. Then we have quantitative and qualitative research. Normally, what we associate is that whenever there is a number, it is a quantitative research. Whenever there is no number involved, it is a qualitative research. Distinction is very clear about it, but no. A quantitative research involves doing some operations on that numerical data. If that numerical data is not able to give any computational results, we cannot do any computation. For example, my roll number may be a numeric value, but I may not be using it. It's a unique value just, to give me an identification. It is not a qualitative, it is not a quantitative variable. It becomes a qualitative variable. And qualitative variables, qualitative research, on the other hand, is concerned with quality, kind, phenomena, which cannot be quantified, which cannot be put into numbers, which cannot be crunched into a number and probably solved with the help of numerical operations. Another word which we use very often is empirical research. We have done, our empirical results show this, and we write this. A conceptual research is one which is abstract theory. Normally social sciences people from management, philosophers, thinkers, they all talk about the conceptual research. But on the other hand, empirical research relies on experience or observations. They regard the systems and theory which are existing, and they interpret those systems and theories in an inference out of it. We'll talk about it in detail when I'm talking about the techniques of research. And of course, there are other types of researches also which are prevalent, like field setting research, clinical diagnostic research, formalized historical research of historical data, the census data of a particular place, the population demographic data of a particular place. We try to analyze that particular data. There are different types of researches. ICT deals with analytical, applied, both quantitative, qualitative, empirical researches. Now, the moment we have understood that we are actually moving on to the research, first question which a supervisor or your teacher asks you, what is the motivation behind that particular research? And you normally mention it in all your research papers, in your thesis, in your dissertations, and everywhere you have to answer this question. In fact, you have to answer yourself that I am moving on to research. What is the motivation behind it? The answer is in this picture. It shows that motivation of a research involves a desire to face a challenge in solving an unsolved problem. So there has to be some unsolved problem, which is of concern with practical problems, and it will solve some problem of the community or solve some problem of some manufacturing concern or some organization. And what do we derive? Why is it called a motivation? Because it will derive an intellectual joy of creating some services to the society or joy for getting a respectability in the organization. So there are a number of things. And it is a section which we include particularly. We should be very clear about why we are motivated, because if our motivation is not above a threshold level, we will not be able to get the best to our research. So it has to cross the threshold level. So that is the motivation of our research, and we have to be very clear about it. When the motivation is very clear, we come on to the steps which a particular research. Normally we confuse in the two things. What is a method? We say, okay, fine, I have this motivation to solve this problem of the organization. So I will be developing some algorithm to solve it. Now this is not a methodology. This is actually a method. So what is methodology? Methodology is a series of steps or phases which we tread on to solve our problem. And each phase may have different technique of solving a problem. For example, if I want to find out evidence or I want to gather a sample data. So there are a lot of ways I can get that sample data. There may be sampling methods for getting the sample data. If I want to, solve a particular problem, may have a mathematical modeling technique to solve a problem. I have a simulation technique to solve a problem, or I have a soft computing technique to make us solve a problem. So that may be the methods. So in each phases of our methodology, we may have different methods to solve a particular problem. And definitely, there has to be some approach of solving these problems. Either I can use a quantitative way of solving the problem, or I can use a qualitative way. About the quantitative way, it may be inferential, experimental, simulation based. We're going to talk about it. And where to use which particular. See, it's very important to understand that if I have a research problem, what is the type of my problem, and what is the right way of approaching that particular problem. There has to be a handshake between the problem and the technique and the methods. We need to understand that, because right approach, right way will lead us to the right solutions. And with this, we are able to find out the two ways. Now, in the books, you will find different types of approaches. Okay, first you do a literature survey, then there is a graph which must be shown to you. Then after the literature survey, you identify your problem. But for me, there is two thumb rules: top-down approach and a bottom-up approach. Now the students come and say, ma'am, how should I approach a problem? What is the problem? Did you identify the problem which you want to approach? No, ma'am, I want to develop a railway system which are efficient metro rail system, whereby the accidents are minimized. Okay. So this is the problem you have identified. Is the problem clear to you? So if the problem is not clear to you, you can move on to a top-down approach. And if the problem is identified, you know this is the problem and there is no solution to it. And so far there is no best solution to it. And I want to venture into the terrain of finding a solution to it. Then you go on to bottom-up approach. And this simplifies our, this simplifies our way of handling a problem or going in, handling a research. So let's see what top-down approach is. Let's take an example. Let's say there is a car, and in that car, you have different systems. You understand that there is a car, and my motivation is that I want to solve some problem of my car, or I want to develop some work on fuel system or brake system and engine system. I do a lot of literature survey and try to find what exactly are the components of the car which face problem. So since cars interest me, so I find out these components as there can be a fuel system which might be creating a problem and I want to mitigate that, or a brake system or an engine system. Even from a fuel system or brake system and engine system, I can once again find out, okay, fine, I'm particularly interested in the brake system. Now the brake system again are of two types, whether it is a brake coil system or brake control system. So my aptitude and interest and my knowledge is more into brake coil systems, and I can mitigate these problems. So I'll try to take up the brake coil system. Now this is something called a top-down approach. I'm actually narrowing down my problem to a small focused area which I want to address. So that is a way of approaching a problem when we are not aware, or we want to explore a problem. We are not aware of a problem, but we know there is a motivation enough to venture into that area, but I do not know where to go about, which problem to handle. So there is a motivation, there is an extensive literature review, we are able to identify the problem gaps. So the moment we move on to the literature review, we are studying these systems. There are existing systems which we are studying. We identify the problem gap out of this system, and there can be several problems. Which is the most pertinent problem? That is what we have to identify. We cannot solve all the problems. This is the time when we have to narrow down our scope. We can take 2 or 3 problems which are achievable, feasible, where we have an understanding of that particular problem, and we select those problems, we formulate objectives around it, we identify the techniques to resolve this problem, and keep revisiting the literature review. Now this is again a very, very important step. We have to keep revisiting the literature review. Why? Because research is not stagnant. Research is moving on. It is very dynamic. People across the globe are working on their research problems. They're coming with solutions. So we have to be aware of what is happening in the community. You have to apply those concepts all the time. So we have to revisit. I want to take up this question. It is something which, in fact, almost every student has asked me. Ma'am, how to identify the problem gap? I read this research paper. It was a brilliant research paper. The author has given the model, author has identified the mathematical modeling aspect of it, given the simulation also, developed that particular model, made a product out of it, everything he has done. But where was the problem gap? I don't know what was lacking in that paper. In fact, that paper was perfect. So, again, there are certain things which are given. There are assumptions, there are future directions. Every research problem has been approached with a definite scope. You need to just envisage your scope. See what assumptions are being taken, where these models will not work. What are the future prospects? What has not been covered in the paper? And this will only come when you do a literature review around that research paper, around that particular topic. Bottom-up approach. Let's say I'll go back to the same question. Like, I know there's a problem in a brake oil system and I want to mitigate that particular problem. So one of the phenomena is to see the brake oil system, what are different types of oiling techniques, what are the greasing techniques, how the two chases work accordingly, and come up what is the friction levels and everything. So I know the problem. But knowing a problem, I cannot just jump onto a solution. I cannot jump onto certain approaches because that is not enough. That time I need to restart understanding that problem in a greater detail, what has been done in past, because we cannot end up doing a research which has already been done or giving it a same solution. We have to think a different way of approaching a problem or a better way of approaching a problem. Give a solution around that particular problem. So we need to build from the bottom to the up. We understand the problem, we do a literature review to verify and analyze the problem. Again, define the scope of that problem, identify various approaches of that problem and solve that particular problem. So we have to backtrack the problem from the bottom of the funnel to the top of the funnel so that we can develop a generalized view of from where did this problem come. Probably that problem has come from the brake system itself, or we can identify if the brake system was involved. Probably that problem is related with engine system. And due to the engine system, this brake oil system is working wrong. So we need to backtrack. And when we explore and unfurl all the facets of problem, then it is much easier for us to mitigate a particular problem. And then comes a very important point that we are moving on to the formulation of research problem. In fact, my lecture is of a longer duration and I think this session is going to end. So I don't know how will I complete it, but then I really want to complete it. So I've just started the whole session. So research formulation, any objective which we form has to be very specific, very much relevant. It has to be measurable. I cannot have a vague objective. Okay, I want to develop an efficient network or energy efficient system. Let's say I have a product and I want to make it energy efficient because it is battery operated. So the moment I talk about this as an objective, it is very vague. What energy efficiency I'm talking about? How much lifetime I want to increase for that particular system? A practical, realistic system has to be developed. Is the solution achievable? Is it time bound? All these things have to be evaluated, and the solution should also be evaluable. The objective can be evaluated. There has to be certain parameters on which I'm able to analyze it. Energy efficiency, does it talk about the battery life or anything else? So we have to talk about that. I just told you about the funnel. We need to narrow down our funnel. And there are so many techniques which are there present. Some say, okay, develop an algorithm. Okay, so ma'am, I will not do a research. I'll do a only simulation-based research. Oh, I can develop a prototype. I'm very good in mathematics and I'll do a mathematical modeling and try to do a solve a particular thing. In fact, my first student who came to me for his PhD, he said, ma'am, I just know genetic algorithm. So my research will be centered around only genetic algorithm. And we later on realized that this is not the approach. The approach has to be that we need to identify the problem as such and identify what are the techniques which are going to suit that particular problem. Let's say we're going to talk about each one of them. Let's say algorithm-based research. Where is it used? Any functional process. If we want to improve a functional process, it may be supply chain, it may be inventory, it may be a protocol, a network protocol. Protocol is just a series of steps. So wherever I require a series of steps or a process, I may go in for an algorithm. Again, then whether that algorithm, what will be the nature of that algorithm? In fact, every topic requires at least 4 or 5 lectures into it. I'm just trying to give you an insight into if this is the condition, this is the technique. That is it, because there are experts who can talk about at length on algorithm-based techniques. I just want to tell you, okay, fine. If there's a process, I need to approach that particular process. I want to make it more efficient, better, reliable. Let me go in for algorithmic-based techniques. And again, with algorithms, we need to understand the type of a problem, the algorithm, maybe polynomial, combinatorial, NP-hard problem. Even if it is a polynomial type of problem, what is my solution domain? If it's a polynomial sort of a problem which can be solved in a series of steps, I can very well go on for a precise solution that is a complete enumeration of solving each and every step, each and every solution, explore each and every solution parameter, and then say, okay, fine, this is the solution which is best suited for my problem. If the polynomial complexity increases and it is not exactly an NP, but still solvable, but is complex, I may go on for a branch and bound one. I may divide my problem into various smaller parts and then approach a particular solution for that. It is a problem which is a very NP hard, very complex problem. It cannot be complexity increases in the exponential form. Then we use heuristic technique. We use a heuristic technique. So there are again different. It involves an intuitive, logic, the heuristic technique, and something like I can identify. Today it is cloudy. It's very hot, cloudy, and the humidity level is very low. Precipitations and the wind is not blowing. The pressure is being built up. Probably it might rain. So that's sort of a logic. Or I may go in for a meta heuristics, or I may go in for a soft computing technique in that. So it involves our knowledge base, our intuition, our logics, and sometimes an analogy also drawn from biological factors or other things. So any process, we need to hook on to algorithm-based techniques. Sometimes people try to see that whole process and try to imitate that particular process through simulations. So when you imitate the operations of a facility or process, normally we use computers for that. So we go in for a simulation. Approach a simulation, we need to understand what is being simulated in the system. For example, if I'm working on networks, I need to simulate a network. There's different simulators present on the network. What are the assumptions? See, a real-time system cannot be simulated. We have to work in a closed box. We have to work with certain assumptions, approximations, some logical and mathematical foundations, models which work into it. So again, there may be two things. A model structure may be quite simple. If it is quite simple, we may use an analytical system, a solution, or devise a mathematical method to get the exact information. But if the model structure is quite complex, then we need to study it via simulation. We evaluate the model numerically, collect the data, estimate the model characteristics, and then try to solve it. Something like this will give you me a guide. It will give us a guidelines. A system So there is a system which may have an experiment. We can do an experiment with the actual system. If it is getting very costly and we cannot afford it, or it is difficult to handle or complex to handle, then we develop an experimental model of that system. And that can be a physical model, sort of a prototype, or it can be a mathematical model. Again, if we are able to develop a mathematical model out of it, we can either go in for an analytical solution if it is simple, and if it is not simple, there are intervening variables in that, we may go in for a simulation. So that becomes a guiding tool for us. We also have another approach, that is we do a prototype modeling. In a prototype modeling, in this particular thing we told you, there is a physical model. This physical model may be called as a prototype, and we develop a small prototype. We establish some outline specifications out of it, develop a prototype and evaluate it. At this particular point of time, we need to take out the prototype and see how this prototype is behaving. We specify and design our system based on that prototype. Nowadays, there are a lot of softwares which are used for prototyping. Blender is there. Then there are all sort of softwares, CAD/CAM softwares, where we can develop a product. You can see the tensile strand before the actual product is being developed or actual system is being developed. So before that, you need to simulate it, find it, develop a prototype, evaluate it, do certain testing on that particular system, at what are the considerations we need to take care of it, we need to design it. But then, why do we do it? It is just that we cannot handle so much of risk of creating a real-time system and then discarding it. It is better to make a small prototype, test it, evaluate it, find out the problems in that particular system, redevelop it, mitigate those problems, and come up with an actual system later on. We've seen the architectures never come with the whole building as such, which falls in one go, but they develop various maps, they prototype it, they study various nuances of it, and then develop a total system. Another approach or technique, mathematical modeling. When do we use mathematical model? A mathematical model, whenever that particular problem is defined as a well-defined math problem, then it is a mathematical problem. A real world problem is quite vague because there are so many competing variables into it. We can work with a set defined boundary of variables in a mathematical problem. That is why, to make a real world problem into a mathematical problem, we come up with certain assumptions. We make it more simpler because we want to see the cause and effect of certain variables only. We developed certain relationship between variables, whether it is a dependent one, whether it is an independent one. So we develop those relationships, come up with certain equations, and we solve those equations to find the model behavior. We test those model behavior with the help of the data, which may be a real-time data. And from the knowledge we acquire from the mathematical models, we transform that knowledge and give it to the real-time systems. That is the implication. We inform the real-time system, okay, these are the variables which affect most into that environment. Fine. For example, I want to increase my profitability. See, when we say mathematical modeling, we have certain decision variables. We have an objective function, that is, I want to maximize my profit. And profit is a function of, let's say, sales and cost. So what is a constraint? Constraint may be a demand. Constraint may be a price, sensitivity of the market. So there may be non-negative restrictions. So we develop the total model and we apply certain techniques. It may be linear programming technique, technique, or game theory, or whatever you want to apply. So it's a mathematical modeling. And it is again polynomial type. But when we say that our problem is huge, it's very, very complex, we do not have any way of solving that particular problem with the exact models, precise models, which require symbolic logic reasoning or traditional numerical modeling and search. then we go in for approximate models, because in approximate models, there are a lot of competing variables. The real-time scenario, real-time problems are being discussed. So these variables may be competing with each other. So you come up with approximate solutions, approximate reasoning, you do a functional approximation, and your search of solution is in very vast area. So you randomly search the solution in the vast area of solutions and come up with certain solutions. Okay, but this is the best solution which is suited. This is an optimal solution which is suited. It may not be the best, but it is an optimal. Given these circumstances, this is the optimal solution. Again, see what all slides I'm showing. Again, soft computing is a very big topic we need to explore, but at least we know that if my complexity cannot be solved with a mathematical problem and I'm okay with an optimal solution, which is a near exact solution, I should go in for a soft computing. It's not that if there is a problem which is very simple, we should jump onto soft computing. No, it can be solved by a mathematical model. Please do it with a mathematical modeling only. It is not advisable to take up the approximate models as such. Then there are different streams: neural network, fuzzy logic, genetic algorithm, hybrid system. In fact, we have speakers, Dr. Anurag Singh Baghel and all will be talking about genetic algorithm, and some other speakers will be touching up some neural network, fuzzy logic, and hybrid systems as well in the lecture series. So these are some of the techniques. Another approach is that why not I do a research using an experimental sort of a technique. I just make an experiment, and since a real-time system will have a lot of competing variables, let me control that environment. Control that environment, just twist some variable some point of time and see the effect of it. So in the experimental, I can control it. So I can just, sensitize one variable and see the result. For example, I'm taking out a experiment with some chemicals. I've mixed 5 chemicals. I just increase or decrease the intensity or strength of one chemical and see the effect on the others, and see, okay, how does it behave in this environment? Or if I make 2 variables and change the 2 variables in certain ratios, what is going to be the impact? So I can conduct certain experiments. Experiments give me more exact nature of results as compared to mathematical modeling and all. We'll talk about it because that is very important to understand. Now, this is something very interesting. It is a guiding map, exactly guiding you to how to approach different types of when to use theoretical research, when to use heuristic result. So I'll be sharing the slides also. So when there is a problem structure, and if I say let me just click the highlighter. So if I say that my problem is transparent, fine. So if my problem is transparent and it is yes, I may go in for a symbolic, and I'm able to go in for a symbolic representation. I'm able to analyze, develop a solution, derive a solution which is analytically feasible. And the computation is not very high, then I come out to a solution. But if the problem is not transparent, my own idea is to develop the problem more transparently. Or probably my idea is transparent, my problem structure is quite transparent, but I'm not able to give a symbolic representation. So I use an analogy. Analogy is you try to understand your system with some analogous system. For example, a chemical engineering student find out some solution and there was a method for it, and it fits well into a mechanical stream also. So mechanical student might try to draw an analogy from the experimentation or from the technique which was taken up in chemistry lab, or it may be biological analogy also, how a particular ant finds out the food. So ant colony optimization or particle swap optimization. So I can draw an analogy from the nature or from simulated and physical methods and develop it. So my symbolic representation was not good, but still I can do it by using an analogy, and this will develop an alternate modeling. Once we are able to develop an analogy, then I'm able to derive a solution onto it. But if I'm able to develop an analogy but not able to derive a solution, I have to use an approximate method, which may lead to some theoretical research, And if the approximate methods are also not acceptable, I may just go in for a pure theoretical research. And if approximate methods which I'm talking about is acceptable, we may go to a non-optimal solution which is acceptable and use a heuristic technique. Similarly, if we can use other methods which like simulation, heuristics, and combine these methods to find out a solution, or if the problem statement is not transparent, it is done through data analysis to make it transparent. If the data analysis also is not able to make it transparent, we do some experiments and make the problem structure transparent. We may use two-step experimental structures or something like that. So this gives you a guidelines out as to how we can actually approach a problem. At every step, I need to find out, is it becoming transparent? If I'm able to make a symbolic representation out of it, if I'm able to derive a solution out of it, if yes, then what? If no, then what? So we have to follow a particular method. That is why research in information communication technology is called as a scientific research, and it is a very planned and stepwise procedure, because we know what are my variable types, how they are behaving, and how to approach a particular problem. Now, in fact, that calls for another session if I move on to explaining the whole thing. Now, research analysis. So, see, once I have find out the right approach of finding, I import a research. I do a research using one of those techniques, and when we get some results out of those techniques, we do this analysis. Operation research techniques for decision making, or when we have to take a decision making, like I can use game theory, I can use linear programming problems or something like that for operation. These are the operation research techniques. Or if it is based on forecasting performance, I may use time series, stochastic analysis and all to analyze my data, or predictive analysis can be, some inferential analysis can be. So there are different types of analysis which can be performed to analyze our data. And that is why we say statistical techniques are used, OR techniques are used, stochastic techniques are used, some predictive techniques are used, inferential techniques are used. So for analyzing the data, because if we can analyze our data, we can better understand our system and we can better present our results. Now, this is a very interesting slide. Why is it interesting is because normally when people develop mathematical model and say, okay, ma'am, I have developed a mathematical model, it was quite an abstract one. Now, if you see the chronological order, mathematical models are the most abstract ones. Analytical models are less abstract, then soft computing, and then real world problems are least abstract. So how to validate? What are the guidelines for validating it? If I have a mathematical model and I want to validate it, I may use a lesser abstract model to validate it or to see the behavior of it. So only giving a mathematical model will not suffice my research. I have to add something more to it. I may develop a mathematical model and simulate it and then see the behavior of it, do the performance analysis so I can justify it. If I have done a simulation, I may do some laboratory experiments onto it and some analyze certain cases onto it and say, okay, fine, whatever simulation I have developed actually confirms or goes in line with my experimental results. You can rely on it. If I do field studies, then I need to observe a real-time system. So a more abstract sort of a system can be using a less. If I'm using analytical model, I may verify the simulation. If I'm using some psychological test, I can do some real world things. So a more abstract sort of a system can be verified and justified with the help of a least abstract system to give a more, provide more verification and validation to my research. Verification and validation of research. Now, normally people say, okay, fine, I have taken the sample. These are some of the questions which come up. Data from somewhere. And this sample data I have analyzed. I've taken it from a research paper and I'm working on the same sample data. But were the assumptions seen? Were the constraints seen? Was the environment seen? All these things need to be addressed. So normally people do is I just compared it with the existing technique or algorithm and came up with my results. But those existing techniques or algorithm or those graphs which we had obtained earlier, will they work? Are they on the same platform or on the same, we can justify our results because they are on the same platform, or probably they are using the same set of assumptions, or they are using the same set of an environment, or they are using the same set of data sets. So if the parameters are equivalent, then only we can go for comparison with existing techniques and algorithms. Otherwise, we cannot. But that can be a technique if we can actually make them at par with each other. We can verify most abstract techniques, the less abstract techniques, this I've already discussed. And another approach which work for verification is our statistical techniques. See, statistical techniques are very, very important. Today we are talking about so many techniques which have been offshoot of machine learning, artificial intelligence technique, and somewhere they borrow the concepts of these statistical and WAR techniques and mathematical modeling techniques indeed. So these techniques can be verified, like we do hypothesis testing, it's a verification sort of a thing. Then inferential testings, then stochastic testings. So all this gives us, we can validate and verify our results with the help of these measures, these things. So our research is incomplete if we cannot justify that our research was right. If we can justify our research was correct, then means we are able to verify it, we are able to validate it. And this completes our research. But imagine I have done a wonderful research, I have come up with a novel solutions, and I'm able to verify it, I'm able to validate it, but it is just lying next to my drawer or in my cabinet, and people are hardly aware of that. Then is this research doing and fulfilling its own purpose? No, it's not. So what do we do about it? That is a very, very important question. We need to make it visible. But before that, let me summarize it. Let me summarize the research process. Normally, we see this particular, flow chart when we go on for a research process in the first group. But I am showing it to you at the last because now you will be able to understand it. Whenever we have a research problem, we need to outline a research problem. If our research problem is not clear, we need to make it more clear with the help of some literature review. So we need to do a literature review to make this problem more clear. We develop a theoretical framework to it. We identify various, when becomes clear, our research problem is more defined. And when our research problem is defined, I move on to the variables. These variables need to be identified properly, which we develop a hypothesis around these models. We may use any of these modeling techniques, any of the techniques, and based on these research, and this whole box, as you can see, is a research problem formulation only. For research problem, it's very important to understand that research has to be problem has to be formulated in a proper manner, because if our problem is not defined, we may come up with wrong conclusions. So we need to define our problem well. If our research problem is very well defined, we may move on to the research design. To construct a research design is like constructing the methodology of our doing the research. Type of research we are going to use, how am I going to measure the design, what will be my sample design, or will I collect the data, will the data come from my experimental or algorithmic or simulation based data results will be there. Then what method of analysis, I'll use a statistical method, or I'll use an OR method, whatever methods I'm going to use. So that all comes in the research design. It requires a proper planning of the various phases. This research design leads to a research proposal. Research proposal has various ingredients. What is motivation? What is the problem? What is the problem gap? Literature review, then objectives, then research methodology, and this whole gamut of activities. And the clarity, so before I start doing the research, the clarity has to be there that I have to make my research design a foolproof one. I'm very clear about where am I heading, with what tools and techniques I am heading to doing my research. Then we developed a research study. This is the main part. Normally, this is the first step which researchers take if they do not know the whole procedure. But if you jump on this step in the first go, you may end up nowhere. So you need to follow all these steps, understand your problem, understand your research design, develop your proposal properly, formulate your problem properly, identify your techniques and approaches properly, test run your approaches, and then move on. Then you actually go in for your research, which may involve some primary data collection, some secondary data collection, some data collection through experimentation, simulation, or algorithm, or prototype. So you collect those data, you analyze your data finally. And here analyzing the data will involve model testing, derivation of relationships, hypothesis testing. So all this analysis will be in this particular phase. And if your problem is solved, you have to report your results and the inferences. And if it is not solved, you have to go back to your research problem, because my results and inferences were not matching to what I thought of what I was aiming at, or my objectives are not being fulfilled. I need to go back and redefine my research problem again, see the variables, dry run my variables. Are they facing any problems? Is the hypothesis right in the right format? Is the proposal, is the research design in a proper format? Is there some problem in the research design? Because I always say a stitch in time saves 9. So if we know, if we have a proper planning, if we have a proper methodology, if we know, is it a top-down approach or a bottom-up approach, if we have done our homework well, we can actually get better results. The probability of failing is much, much less. I will not say that you will succeed always, but you will know 1,000 ways or 100 ways, whatever you have tried of failures, that these are the ways which are not going to succeed. You have actually identified that. Which is very, very important. If I do a research, I present it well, I need to put it into a report. I need to publish it. I need to file a patent against it. I need to write a white paper. Because if my research is not visible, it is just like a bulb. It is lying dormant in your alley or your corridor, and it is not showing a light to anybody. No direction is being sought by that bulb. So you need to make it visible. Again, there is a complete lecture on how to make your research more visible. In fact, we take 2-3 classes on report writing, publication, how to file patents, how to write a white paper, what are the ingredients of a white paper, summarized how a report has to be compiled. So all these things are very, very important. How to write a research paper, in fact, and it's not, I normally use this quote that life is too short to experience everything, learn from other mistakes. When we hear people saying, okay, he's so young, he may not be knowing what research is all about. But if you are capable, you can understand what mistakes people have done, you can go through that, you can well equip yourself, you can avoid those mistakes. It's not that you have to spend another 10 years to learn how to do a research. You have to analyze and understand how the research was being taken by other people. Take their experience into the account. That is why these slides which I made was just out of my experience, not from any book. Though I took one or two definitions on the first or second slide just to show it to you. But all these slides, if you follow to the core, I believe you can move on to your research and give some meaning out of it. I have hurried on to my presentation because the time limit of this, session is of 40 minutes. I think I am just nearing to the end of my session. So I have tried to, rush through certain slides like soft computing, algorithmic research, mathematical modeling. I could have taken up an example and explained it further. But if in these expert lecture series, if it is required by the participants that I should speak on to a particular topic, I'll definitely love to do so. And you can get back to your coordinators on that. Thank you. And it is just the beginning of our series of lectures, expert talks on research techniques in information and communication technology. There is an echo.
Thank you, Vidushi ma'am. Are you able to hear me?
If participants have any queries, they can unmute their mic if they want to raise hands. That will be great if they can raise hands and ask it. If there is no queries, we can move on to the next presentation. Yeah. Anybody?
Thank you.
I can see some queries in the chat box. There is a question. Please touch on the topic of marketing perceptions in advertising in the upcoming sessions. Okay, this is for the upcoming sessions. Okay, thank you. So no queries in this particular session. Thank you so much. And if you have any query in any of these lectures, please let us know. Thank you so much.
Thank you, ma'am. So we will be rejoining after 1 minute. Thank you so much.
Thank you.